Whatever floats your biscuits. So let's make up a rocket question. Let's say we have so the rocket engine fires and provides I don't know. Let's say the rocket engine fires for 2 seconds, providing a acceleration of 4 meters per second squared. After the 2 seconds, the rocket engine shuts off and the rocket continues to its highest point due to free fall. Now, drawing the picture changes the demeanor of the question. If I didn't draw the picture, you might understand that there are parts to the problem. And in those parts, you may not be able to see the details unless you draw a picture. So I'm drawing the picture as I discuss the problem. But in this problem, what I would be asking you guys is, what is the maximum height attained by the rocket? And what is the time that the rocket spends in the air? And I'm specifically asking those questions because you have to make a certain number of mental connections to understand how to deal with this question. So the problem wouldn't have a drawing with it to indicate where the separate parts are. So in this question, you're expected to recognize that there are really 3 different parts to this problem. There is the time in the problem where the rocket is under propulsion and is experiencing 1 acceleration. There is the time in this problem where the propulsion has turned off and is experiencing a different acceleration. And then there's the time in which the rocket falls back to the ground, still experiencing the same acceleration as when it was moving upwards. Now, you have options on how you can move forward to solve the questions of how high does it go and how long is it in the air. There's not a single right way to go here, but probably 3 or 4 different ways you could get to each of these answers. I'm going to present the same way that I did the last time. Or maybe I'll change it a little bit. I don't know. I'll tell you what, I'm going to change it a little bit. I want to prove that you don't necessarily have to do it the same way. I'm going to break the problem up into these 3 parts. There's the part where the rocket engine was firing. There's the part where the rocket engine had shut off, but we have not made it to its maximum height yet. But there's also the part where the rocket engine shut off, the rocket went to its max height, and came back to the ground. We can find all of that time in a single effort. So I'm just going to do the problem a little differently than I did it last time, just to offer you an alternative. And I'm going to say that these are the 3 parts of the problem that I'm going to do. You don't have to do it this way. The way I did it in class was a little bit different. But this is the way I've decided to do it. Now, what you might not understand is that each one of these parts is probably going to require its own set of motion variables. If it hasn't come through yet, let me kind of just hit you over the head with it. You need a different set of motion variables for any 2 time periods being observed, anytime there's different accelerations being observed, or anytime there's different displacements being observed, or any combination of the 3. So in this case, there are different ways to break this problem up, but each one of them is going to require a set of motion variables that we will then use to kind of solve for missing information. So I have one there. one there, one there. And just to be clear, displacement, initial velocity, final velocity, acceleration, and time. Now, here's where I think we stop and pause and make a couple of decisions. 4 of these are vector values. And because they're vector values, they beg the idea of direction. We're doing one-dimensional motion right now. So because it's one-dimensional motion, direction is completely handled by whether the value is positive or negative. So you need to identify what direction you want to call positive. And you don't have to be the same throughout the entire problem, but it's probably better for you if you are. So do you want up to be positive or down to be positive? Okay. So I'm going to make down positive because all of you want up to be positive, and I'm doing it on purpose. Anybody who's been in physics before knows that the acceleration of gravity shows up many places throughout the course of this year. And if you're not careful and you always make up positive, you might become complacent and begin to believe that the acceleration of gravity is negative. And it is not. The acceleration of gravity is downwards. But you tend to confuse downwards and negative because you have a misconception about what negative means. So I'm going to purposely flip the script on this problem. Because we're doing it for a second time, not for everybody, but for many of us, I think that's okay. Now, by doing that, I am going to have to point out that I believe after the first 2 seconds, the rocket will have a velocity in this direction. Agree? At its maximum height, we know that the rocket will have a velocity of 0. That's the only way we know to be at the maximum height. Again, that's a piece of information that should be in your notes somewhere. That in problems that involve looking for a maximum, maximums occur when that number can get no bigger. So we have to wait until it stops going up. The instant it stops going up, we're at the maximum height. That occurs when the velocity is 0. So let's start with this set of motion variables. We don't know the displacement, and we know the initial velocity as rest. It's starting from the ground. It experiences an acceleration of 10 meters per second squared and does so over 2 seconds. Now, just to be clear about what I'll be looking for tomorrow when you guys take your test is organization. So can you organize yourself? Can you read a question, take information from the question, and use it correctly? I'm giving you a framework to make it easy for the person who grades your test to see the information as you've presented it. Yeah?
Why is the acceleration 10 if you said it was 4?
Because I'm not thinking clearly. So I want to make sure you understand that you need to present some kind of organized bits of information. If you skip this part and go right to solving equations, that is okay, ultimately, as long as the person grading can find your line of reasoning. If the person who's grading can't find your line of reasoning, they may not issue you the points that you deserve. So just be careful. Give yourself time to organize. Now, part of organization is assessing direction. 4 of these motion variables require that you consider whether they should be positive or negative. In the case of this problem, we said upward is negative, so my acceleration is negative. Back to where we were. Looking at the information I've gotten down, it's clear that I could use this to figure out what the displacement is while the engines are firing and how fast the rocket is going at the end of the interval when the engines shut off. That's information I could figure out. Now, do I need either of those pieces of information? Now, that's where you have to kind of figure out what to do with the problem. Clearly, yes, I'm going to need to know how high the rocket is. But what you also probably have gathered is that the rocket doesn't instantaneously stop because the engine's shut off. Something has to bring the rocket to rest, and in this case, that's going to be gravity. So when the engine's shut off, it becomes a free fall problem, and gravity takes over the acceleration downwards at 10 meters per second squared during this next interval. Now I know the final velocity over that interval is going to be 0. The acceleration is going to be 10 meters per second squared. It takes me, the problem solver, to recognize that the rocket enters this section with an initial velocity equal to whatever it exits this section at. Meaning it acquired velocity while it was accelerating upwards. It has that velocity now, and gravity is going to bring that velocity back down to 0. So I want to make the connection that whatever I get here is going to be used there. I think this is a pathway to figure out how much further the rocket goes into the air. Thus, I can figure out what the total displacement of the rocket is. So let's execute on this. Before I do, let's deal with direction. I'm pretty confident that when the rocket engine shuts off, the rocket's going to have a velocity that is upwards. That means this number is going to be negative, even though I don't know what it is. And at the same time, the acceleration is downwards, so that acceleration has to be positive. And that's enough. Let's work this problem out. I need something that gets me the displacement and something that gets me the final velocity. So let's deal with the displacement first and ignore the final velocity. That sounds like this relationship would probably be the most likely one to get us there. I will allow a 3x5 index card on your test tomorrow. Again, I don't want to do the math. I'm only doing the math because I need you to see something. But ultimately, I would generally not want to do the math. 2 squared, 4. 4 times 4, 16. Half of 16, 8. So I'm pretty sure we're looking at a -8 meters here. So negative is upwards. So I get a displacement that's negative. It just tells me that it's upward. You can get rid of the negative sign and write the word upward, and it means the same thing. Remember, positive and negative are just about direction. It's a number line. I will need the velocity too, though, so might as well take a minute and do that. So if I ignore displacement, I would use v squared minus v naught squared equals 2a delta. Oh, wait, I don't want to use that one. What am I thinking? I want to use delta x. No, I don't want to use that one either. I want to use v equals at plus v naught. Now, the truth is, I could have used any of those. I'm choosing to use the one that uses the given information, not something I solved for. Either way, though, this is pretty straightforward. V equals -4 times 2, or -8 meters per second. Again, not surprised, when the rocket finishes firing its engine, it's traveling upwards at 8 meters per second. That's what the negative means. Now, that 8 meters per second now gets applied here. And we're going to use that to figure out what the displacement is. I need a relationship that has those 4 things in it. And I think v squared minus v naught squared equals 2a delta x. So 0 minus -8 squared equals 2 times 10 times delta x. I'm trying to be super careful about this because people have this idea that this negative sign somehow gets squared, but it doesn't. Yes, sir?
If you got v equals -8 squared, why did it go into
I'm sorry, you'll have to say that a little bit louder.
if you got v equals -8, why did it
the v here is the final velocity for this interval.
Obviously.
And that becomes the initial velocity for this interval.
Ah,
Is that okay?
yeah.
All right. Again, this is just math. It's not very interesting to me. 8 squared is 64. So I think delta x will be negative 3.2. So I'm just trying to do the math in my head, but 64 divided by 20, I'm pretty sure is 3.2, but I have to retain the negative sign. So negative 3.2 meters equals delta x. Now, again, negative, not a surprise. It kept going upwards into the air. So we tend to be fixated on positives going up. And that's why I'm choosing to do this problem this way. So at this moment, the rocket is 11.2 meters in the air. That is the maximum height obtained by the rocket. 8 meters plus 3.2 meters. But now, we want the time that the rocket spent in the air. So let's take a look at just this part. This initial velocity is the same as minus 8 meters per second from before. Right? We're dealing with the same velocity the rocket had when the engine shut off. So minus 8 meters per second. I don't know how fast it's going when it reaches the ground. But I know that delta x is going to be whatever this distance was, and that was positive 8 meters, because it is 8 meters above the ground, and we said downwards was positive, so this displacement will be positive 8 meters. And the acceleration, well, that's going to be 10 meters per second squared. And that's also downwards, so that's positive 10 meters per second squared. And we want the time that it's in the air. Any questions about any of these choices? All right. I think delta x equals 1/2 a t squared plus v naught times t. So 8 equals 1/2 times 10 t squared minus 8t. Now, I've put you in a bind doing it this way. If we had found out the amount of time it takes for the rocket to fall from the very top to the ground, from here to the ground, you wouldn't have been stuck with a quadratic that's like this. By doing it this way, we get a regular full-on quadratic, which is harder to solve. I'm okay with it. If you're not okay with it, then break it up into 2 parts. But if you break it up into 2 parts, you will have to go back here and figure out the time, because you're going to need that too. I'm just doing it this way, because I'm not scared. Let's be honest, you won't raise your hand for this, but if I asked you guys who's scared of using the quadratic formula, it's actually a bunch of you. Or else you wouldn't have asked if you could put it on the back of your note card. So that suggests maybe a little bit of nervousness about using it. I don't know why, but get over that. So I'm going to write this different. I'm pretty sure it does not factor. What's that?
I said I think it's more just like lazy than fear.
Oh, I think you're probably right, but I didn't like to say that. I don't want to be that negative. I still say the best way to do the quadratic formula is just do it in your head. I mean, not in your head. Do it longhand, writing it down, a couple of steps. Don't try and push it all into your calculator. So negative b plus or minus the square root of b squared minus 4 times a times c, all divided by 2a. There's nothing special about this, and everybody who tries to kind of cut around it by making somebody else do the work for you, usually your calculator, it doesn't make it easier. 4 times 8 is 32. 5 times 32 is 160. So plus 160. All divided by 10. You can check my work on it. I think I'm right though. Because 4 times 8 is 32. Whenever you multiply by 5, it's like doing a half. So half of 32 would be 16, but add to 0. So that's got to be right.
You do 20.
What's that?
You do 20 times 8 also.
Okay, that works. 64 plus 160 is going to be 224. So this is 8 plus or minus square root of 224 over 10. Now, 224 is really close to 225, so this has got to be 15, or really close to 15. I'm just going to, yeah, so it's 15. It's good enough for me. Yeah, 0.996, that seems like 15. So 8 plus or minus 15 over 10. Clearly, I'm going to throw out the one that's 8 minus 15. But the 8 plus 15 works out great. So 8 plus 15 is 23 divided by 10, 2.3 seconds. This is not the answer. It's close to the answer, but it's not the answer. The total time in the air is 2.3 seconds plus the 2 seconds the engines were firing, so 4.3 seconds. That's the answer. This is reasonable for your test. It's a lot though, and we've done the problem many times. Yes, ma'am.
Why wouldn't you use the time from the second one?
Because this includes that time.
And it does?
Yeah.
Oh.
Yeah, by doing this one, it will include time. If you'd like, we can do it the other way, just so you can see that it includes the time. It's not hard. If we do it the other way,
I think it's because I can't see the wording, so I just forget what you said.
sure, but just find this t.
I did.
And what'd you get?
0.8.
0.8? So seconds, so that's this time. So now, if we were to try and do just the fall portion, just the fall, that's 0. Acceleration is 10 meters per second squared, and the displacement is 11.2. And now you're solving for the time. You won't have to do a quadratic this way. So you'll get 11.2 equals 1/2 10 t squared plus 0. So, what's that? 1.4? Okay. So 1.5 plus 0.8 plus 2, yeah, same. Yay! So, is this one hard? I think it's hard if you don't know how to break it up into pieces. I think that's the secret. That's what makes this a problem and not an exercise. It's filled with 5 or 6 exercises, isn't it? Once you can identify the 3 pieces, you got to do that exercise over and over and over again. But I say this is a problem because you have to know how to use the information you solve in one part correctly in multiple parts towards the future. So it's tough. It's tough. Is because I chose to use this state of the problem where it's moving upwards with an initial velocity, the displacement from there to the ground, and the acceleration that was acting during that entire time, which was the same acceleration for the duration of that time. Breaking it up into 2 parts and finding out the time to get to the top and the time to go from the top to the bottom won't change the fact that it was the same acceleration and the same conditions. The only difference is that by breaking it up into a part where I get to the maximum height and the part where I go from the maximum height to the ground, it takes what is a quadratic, a parabola, and separates the parabola into 2 parts. And you're finding one part of the parabola to get to the maximum/minimum, and the other part of the parabola to get to some other portion of the curve. But the time would have to be the same. whether you break it up into two parts or not. I'm not sure if that's giving you a reasonable explanation as to how I know, but it's ultimately, it's because the other parameters were the same. Same initial velocity, same acceleration. Whether you're breaking up into two different displacements or not. Keep going. I'd be happy to answer other questions on the homework or on the practice test. Yes, ma'am.
Just a question about the practice effort here. When it just says write a mathematical model, do you just literally mean write the formula that you would use to find?
The specific one you should be using. So, write a mathematical formula. It's
Just write a
right,
mathematical
right.
model for the car system.
I would hope that some of this has come to you guys because you guys have looked at the lab work a little bit. But for all situations in which the acceleration is a constant, in every situation where the acceleration is a constant, the velocity versus time graph has to be linear. Correct? Regardless. So the model that would have to describe this graph has to be a model in which we are looking at something that is linear. Well, what is this graph but a function of the velocity for every point in time, where velocity is plotted on the y-axis, time is plotted on the x-axis. So what are my other variables? Well, this one has to be the initial velocity, and we know by definition that the slope of the velocity graph is the acceleration. This is the model that must be used if you want to express the model that describes the velocity as a function of time. Now, advance one step further. What if they ask for the position as a function of time? Well, we should be aware that if I was looking for the position as a function of time, right now, I could model it by recognizing the initial velocity was negative, point here on the position graph with a negative slope. There's some future point in time where the velocity is 0, and I would have traveled a negative displacement because that's a negative area. And then it seems to be there's going to be some other point in time where the velocity is positive. This is clearly quadratic. Right? Do we have a function that describes this? Well, sure. Y equals ax squared plus bx plus c. But for us, we're plotting position on the y-axis, right? And on the x-axis is time. So what do these variables stand for? Well, we've got a clear idea of what it should stand for just by looking at our motion equations. C has got to be the initial position. B has got to be the initial velocity. And we know that A isn't the acceleration, but half the acceleration. This is the model that we would apply to a position graph. It tells us the position as a function of time using nothing but initial conditions, which is why I stressed to you guys that these functions are the functions that I think we need to kind of be careful about. These are the more important motion equation functions because they're actually motion equations. The other ones are just equations. They're not functions. So this is why these can graph and tell us about the events and are the shape of the position and velocity curves. So when you're asked to give an equation that describes a function, these are the ones I'm looking for. That's why we did the lab where you had to apply the function to the curves. Right? The car lab where you had to do the velocity graphs and the position graphs to get you accustomed to the idea that that's how you get it. I think there's the question I gave you guys look like this. Let me just move this out of the way. In the actual practice FRQ, -4, or no, I'm sorry, +4, -14, 3 seconds, right? You're asked to produce a mathematical model for the position graph. I'm not sure it occurred to you how you could do that without really doing very much work. The initial velocity is +4. Meters per second. The slope of this graph is -14 -4 over 3, right? This point, using both of those to determine what the slope is. And slope is acceleration, so the slope was -6 meters per second squared. And that slope is the acceleration. So my mathematical model, x minus x naught equals 1/2 times -6 t squared plus 4 times t. That's all you have to do for a mathematical model. But this is the mathematical model in the same way that v equals -6t plus 4 would be the mathematical model that would describe the velocity. Questions about that? Alrighty. All right, so you're standing in front of a 1.5 meter tall window. You see a rock pass by the window, and it takes the rock 0.4 seconds to make it from the top of the window to the bottom of the window. If the bottom of the window is ground level, how high was the rock when it was dropped? I encourage you to do a couple of things in any problem like this, and that is draw a picture. You guys, you want to convince me, and not me so much, you want to convince the person who is grading your paper that you know some things about the problem. A picture is an adequate and maybe even a beneficial way to do so. So I would start by recognizing that if I draw myself a quick window and I could, identify that this is 1.5 meters. The rock was started here, some point above the window. And from the moment it appears in my view, for it to go from here to here takes 0.4 seconds. And the problem asks, how high above the ground was the rock or the ball dropped? So that's the setup to the problem. In determining how to solve this question, I'd argue that this isn't an exercise, this is a problem, and that this is a problem that has several exercises involved. So I notice that there's two different displacements being discussed. There's a displacement of the ball as it passes by the window, and then there's the larger displacement of the ball from where it was released to where it struck the ground. Would you guys all agree with that statement? So I see two sets of motion variables. One set of motion variables that describes what we see in the window, and one set of motion variables that describes the entire motion of the ball from the moment it was dropped from rest. There's different ways to do this problem. This is the way I've decided to do it based on the way the problem was described. But you could break this problem up into different ways. Like you could have broken, because we did this problem in class, a similar one. You could have made this your delta x and considered the problem starting from there. I am doing what the problem asks, which has to do with the larger problem. Now, before I go on, I think it prudent that I identify what direction I'd like to call positive in this problem. So would you guys like up to be positive or down to be positive? Excellent. So down is going to be positive. And this is purposeful. You guys need to become adaptable. And more importantly, there's a couple of you who already know this to be true. If you begin to become complacent, that downward is always negative, you might believe that g is negative 9.8 meters per second squared or negative 10 meters per second squared. And that's wrong. G is 10 meters per second squared directed downwards. If you start associating a negative with it as if it's a negative number, you will have the wrong concept in your head. So you're going to have to deal with the fact that this is a decision that is arbitrary and does not affect the outcome of the answer. So since all of you wanted it up, we're making it down. Okay? Let's deal with, this is the window portion. And this is the whole thing. In the window portion, I notice that the rock travels downwards 1.5 meters. It's downwards, so I'm making that expressly positive. Also, it's accelerated by gravity. Gravity is also downwards, so that's positive 10 meters per second squared. And lastly, it takes 0.4 seconds to make the trip. Now, I've done something very important here, and I'm not sure that you guys understand why. I put the positive signs next to everything that was a vector quantity. This is telling the person grading your paper that you have taken the extra step to think about the direction of each vector. If I'm going to issue points for a problem like this, it's not for the answer. The answer is probably the least impressive part of this. Although it's easy to grade your work if the answer's right, it's more often that I'll grade a paper where the answer isn't right, but many of the things you've done were correct. You believe it or not, most of you get knocked out because of poor arithmetic. But if all you show me is the answer, you'll get 0 out of whatever points. It's your job to convey to me what you do know. Based on what I'm seeing here, I think we got 2 to 3 points just being conveyed by you knowing how to organize the information that was given. And maybe another point for understanding that it's your responsibility to deal with direction and to identify how you're going to deal with direction to the person grading. So if the whole thing's maybe worth 5 or 6 points, way more of the points is going to be wrapped up in your ability to organize and disseminate the information that's given. Because there's not going to be a picture. It's all going to be some paragraph, and you're going to have to extract the information. Now, to continue down this road, I do realize I could find either of these 2 pieces of information. And in this particular portion of the problem, this is the V naught, and when it's down here, that's V. Now, I don't want any of that information. I was asked where the rock was dropped from. That's ending a sentence with a preposition, which is terrible grammar. So I was asked from where the rock was dropped. That's appropriate grammar. So I'm glad I corrected myself. Is there a piece of information that I could use to figure out from where the rock was dropped? Yes, sir.
The initial velocity of your window section will give you the final velocity of the area before it came into observation before the window.
That's true. I could use the fact that the rock acquired velocity in going from here to here. However, this velocity isn't a part of this displacement. If I do it that way, I would be finding information related to this displacement, which I could use to get the answer, correct? I could add that to the 1.5 meters, and that would certainly do the job. I'm going to purposefully do this a different way, since this is the way we did it last time. I'm going to use this velocity. And the reason is because the final velocity for the interval where it's in the window is also the final velocity for the entire fall. It's going to give us the same answer. I'm just going to save us one step. Now, let's go ahead and find that final velocity since we have all the key components necessary to do so. That'll be delta x equals vt minus 1/2 at squared. 1.5 equals v times 0.4 minus 1/2 times 10 times 0.4 squared. This is the arithmetic portion, and I am totally not into the arithmetic. 0.4 squared is 0.16. Half of 0.16 is 0.08. 10 times 0.08 is 0.8. So that's going to make this 2.3 equals v times 0.4. And that makes v equal to, I don't know. Somebody will do it. 2.3 divided by 0.4.
5.75.
5.75. Comes out positive. Positive checks out. The rock is traveling downwards at 5.75 meters per second when it hits the ground. Excellent. That also means that this is 5.75 meters per second. This acceleration, positive 10 meters per second squared. And I know it was dropped from rest. Yes, sir?
Unless specified otherwise, does dropped always mean dropped from rest?
Yes. Yes. I haven't checked, but I'll make sure that there's no ambiguity on the test like that.
Because problems you've given us thus far have been very specific with that. They say dropped or they say thrown downwards.
And that should be the goal. That I'm thinking we've got a method to get to the answer here. I think at this point we're kind of done. I don't know that you need me to do the arithmetic, but I will at least point out that this is the likely path to get to your answer. And 5.75 squared minus 0 equals 2 times 10 delta x. So, I don't know what that is. But I'm confident that you guys can figure it out. Arithmetic doesn't interest me. I will point out this, though. Delta x should be in meters. And because of displacement, you should indicate that the rock fell downwards this distance, but that's not what you were asked. You were asked how high above the ground it was dropped. So any reference to that plus the unit will be fine. You won't get the point here unless both the number and the unit are correct. Yes, sir?
So if it's like 10, would it be negative 10 meters?
No, the question asked how high above the ground or where above the ground it was dropped. You could say negative 10 meters, or you could say the rock fell a total of whatever meters. That part is not intended to be ambiguous or to try and trick you. I would be more concerned that you guys get directions of velocity and acceleration correct. But, all right. I think you have to bring something to this problem, and if you can't bring it to the problem, you have difficulty. And that is, we're somehow on a ramp, and that ramp has the same inclination in the first part of the problem as it does in the second part of the problem. So we need to know what the acceleration is for objects that roll down the ramp. So that's what the initial information is about, having you work out what the acceleration is for an object that has just rolled on the ramp. So let's deal with that first, because we need that acceleration. And I don't even think I hardly need a picture for this, but I will still provide one. You roll a ball up a very long ramp, and you are told that when you roll it up the ramp at whatever the starting velocity is, it will travel a distance of 10 meters and will take 10 seconds to reach a final velocity of 0. We're going to need the initial velocity, because we use that again, and the acceleration from the ramp. So this is an exercise, this first portion. I will make up the ramp positive. Displacement, positive 10. Initial velocity, unknown. Final velocity, 0. Acceleration, unknown. Time, 10 seconds. Since we need both the initial velocity and the acceleration, we'll have to solve for them separately. Let's solve for the initial velocity first. I would use delta x equals 1/2 v plus v naught times t, or 10 equals 1/2 0 plus v naught times 10, which suggests my initial velocity was 2 meters per second. I need the acceleration, so I'm going to ignore the answer I just found and assume that I don't know it, and I'll use delta x equals vt minus 1/2 at squared. I'm going to use this to solve for the acceleration, which is going to be 10 equals 0 times 10 plus 1/2 a 10 squared. 10 squared is 100. I'm sorry, there's a minus sign, and I put a plus sign. So 10 squared is 100, half of 100 is 50, 10 divided by 50 is 1/5, or negative 0.2 meters per second squared equals the acceleration. So down the ramp. That's how I'll interpret that negative sign. So now I know that down the ramp, 0.2 meters per second squared is the acceleration of the ramp. Any questions about what I've done here? All right. I don't need that information anymore to do the next part of the problem. So this can all go away. And let's consider our new problem. A sled is started on the ramp. So whatever that means, a sled. And a sled begins sliding down the ramp from the top at a speed of 2 meters per second. You roll your ball towards the sled when it is 10 meters away. I'm going to complete the question. If you wish to leave, go ahead. I will post this later. If you're staying for tutoring, then hang out. But try and be quiet as you exit. Good luck tonight studying. You roll your ball towards the sled when it's 10 meters away from you with the same speed you used originally. When does your ball pass the sled? You too. Bye-bye. This is all the information that we have in the problem. So I see two different objects, so I'll have to analyze the two objects differently. So picking up where we left off, I need to identify a direction that we're going to call positive, and I am indifferent about which direction we call positive. So what do you guys want to use? There's really no advantage one way or the other. All right, so up. All right. So sled, ball. I'm going to make, and we need to choose this too. What would you like to make the origin of this problem? The sled or the ball? The ball? So the ball is at the origin at time 0, and that means that the sled is at 10 meters at time 0. I'm going to start with the sled. The sled displacement, initial velocity, final velocity, acceleration, and time, but constant velocity. So the velocity is negative 2 meters per second. Final velocity, negative 2 meters per second. Acceleration is 0. So delta x equals negative 2t. Okay? Now, the ball. Delta x, v naught, v, a, t. Initial velocity is 2 meters per second. And it's up the ramp. Acceleration is negative 0.2 meters per second squared. And that's all we have. So delta x equals 1/2 times negative 0.2 t squared plus 2t. Now let's be mindful of delta x. These two objects did not start at the same position. So delta x for the ball is going to be x minus 0. Delta x for the sled is going to be x minus 10. We good? So I can go on? All right, so that's it. I have two equations and two unknowns. X equals 2t plus 10. I'm going to sub that in here. I'm running out of space, so I'm just going to bring this down and have 2t plus 10 equals negative 0.1 t squared plus 2t. Now, clearly I can subtract 2t from both sides, and that goes away completely, and I get 10 equals negative 0.1 t squared. And you're going to notice something, I think, pretty important here. There is no answer. All right? Yeah.
If it was delta x equals negative 2t, then that should not be x
Oh.
equals negative 2t.
Yep.
plus 10.
Mr. Shelton should do his math better. I still think we're going to get the same answer, but you're right. So I forgot to bring the negative side down. I still think we get the empty set for the answer, but I'm not sure. Now I'm not sure. All right, so unfortunately, since you pointed that out, I have to do all the work. That's okay. 0 equals negative 0.1 t squared plus 4t minus 10. That good? Quadratic formula is all we got here, right? So negative b plus or minus the square root of b squared minus 4ac divided by 2a. So 4 times 10 is 40. 40 times 0.1 is 4. So I get 16, negative times negative and negative, so it's 16 minus 4. So this is minus 4 plus or minus the square root of 12 over 2 times negative 0.1. We might get a real time. All right. So the root of 12 is 3.5. 3.3, I don't know. 3.46, so 3.5. So I'm going to have minus 4 plus or minus 3.5 divided by negative 0.2. So I have two positive times. So I'm going to have 2 times in which the ball passes the sled. The first time is going to be when I subtract that, I get negative 7.5 divided by 0.2, so that's negative, it's hurting my head here. You guys do the arithmetic for me. So negative 7.5 over 0.2, negative 0.2, and of course, negative 0.5 over negative 0.2. Those are my 2 times. And they're both positive. So I guess we're going to pass it once when the sled's going down and the ball's going up, and we're going to pass it a second time when the ball's had a chance to stop, turn around, and come back down and meet back up with the sled eventually. So I don't know what these 2 times are, but that doesn't actually answer the question. To answer the question, you'll take each of these times and plug them back either for the sled here or for the ball here. If it were me, I would use the sled's function. It's easier. But it doesn't make a difference to me. Yeah? I thought you had your hand up.
No,
Is that sufficient? Or do you want more? That's the answer to that question.